Hello everyone, my name is Brandon Bills. Today I'm going to talk about untargeted analysis and how you can use real-time library searching to give an instrument a little bit more guidance so that your final results will have the most relevance possible. Background about me, I am a product manager at Thermo Fisher Scientific based out of San Jose, California. I've got a PhD in analytical chemistry, and I am the product manager for the Thermo Scientific Orbitrap IQX Tribrid mass spectrometer. So first, we'll start off talking about what is real-time library search on the Thermo Scientific Orbitrap IQX Tribrid mass spectrometer. This will include how does real-time library search work, how do I add it to a method, and what are the different settings that can be used to change how it behaves. Then we'll move on to a real-world example with one of our collaborators, specifically where we were studying indole compounds. That will include talking about what are indole compounds, how real-time library search changed the acquired data, and how real-time library search then changed the final results. So first off, what is real-time library search? Well, RTLS is a filter. And if you're familiar with our drag and drop user interface for our method editor, it will sit beneath MS2 and act as a gatekeeper saying yay or nay, you can run the experiments that are after this filter. You give it a library as well as score thresholds. These are typically determined empirically. We'll talk more about that later when we're going through the real-world example. And it's there to say you should only spend instrument time running what's beneath this filter if it meets your criteria. Within the real-time library search node, there are a number of settings to tell the instrument how to make use of the library that you've provided. At the top here is where you enter where locally the library is stored that you want to use. It's going to be a local file with a .db suffix. This is either something you've curated locally or an offline version of MC Cloud. Next, we have the setting tolerances. This is how close the settings in the experiment need to be to the library for it to be considered a valid comparison. For example, the collision energy tolerance means that the experimental collision energy must be within this value of the library collision energy, or it's not considered a valid comparison for generating a score. The precursor search tolerance in a similar vein means that the precursor from the experiment needs to be within this mass tolerance in ppm of the library precursor for it to be considered a valid comparison. Now, if you're doing a similarity type search, this removes the precursor search tolerance altogether because you are just comparing fragments. We'll talk more about similarity searches later. The fragment ion index gives you some finer control about how the instrument uses the fragments within the library. For example, the minimum number of matching peaks between the experiment and library means that you must have at least that many peaks matched or it won't generate a score. For example, this says 4, so you must have 4 fragments that are in both the experiment and the library or no score will be generated. Next is the minimum library fragment ion intensity contribution. This simply means that you must be of this relative abundance or higher in the library in order for it to be considered a valid fragment to take part in the score. In this case, 0.05 means it must be of at least 5% relative abundance in the library, or it won't be used to generate the score. The number of experimental peaks considered is pretty straightforward. That's how many experimental peaks are being used to generate the score. This is set to 100. That means the top 100 peaks will be used to generate the scores. Next checkbox, use ADDX for offset query searches, lets the instrument know that you want it to consider comparisons against mismatched ADDX. For example, let's say you find the sodiated version of the compound in your sample, but the protonated form is in your library. What this does is when it's looking at what compounds it wants to consider generating scores for in the library, it will look for both the base compound, so protonated versus protonated, but it will also change the precursor mass of what's in the library by the difference of a protonated versus a sodiated, or whatever adduct you're using, and use that as another valid comparison for generating a score. So if you've got a sodiated form that shares fragments with the protonated form, it can still trigger additional scans. The adduct masses table lets the instrument know which adducts you want to consider. By default, this is set to M, which is all protonated species, and 0, which is all charge states. Next is the maximum search time. Whatever you set this to, if the instrument reaches that time while it's generating a score, it will give back a null result and move on to the next compound. So long as you don't set this to an extremely large value, such as longer than the cycle time, it should not impact the scan rate of the instrument. The checkbox at the bottom allows some additional behavior. The retention time filter lets you tell the instrument to check the retention time metadata field in your library and use that as another criteria for what is a valid comparison. Reverse library search changes the scoring algorithm, and we'll talk more about what is forward, bidirectional, reverse library searching in a later slide. At the bottom, we have use multiple precursors to check other precursors that were co-isolated in the MS1 isolation window, and consider all of those as valid comparisons in the library. We have the peak selection and threshold settings. Now, this gives the instrument more guidance on how to use the results and what thresholds it needs to pass. At the top, we have a list of checkboxes that will guide the instrument on what to do with results. If it's checked to be used as trigger only, that means this filter will only say yes or no. You can move on to the nodes that are beneath this filter. If you leave that unchecked, you can check consider unmatched peaks only, which will allow you to influence MS3 behavior. What that means is when it gets to MS to the third, if you've got this checked, it will say, okay, I want to target the unknown parts of the structure. The MS2 in the library that match the MS2 in my experimental represent things I already know about the compound. The unmatched peaks I don't know about, those are the ones that we should be collecting MS3 data on so we can figure out what those are. Add adducts to dynamic exclusion allows you to say, if I've triggered on the sodiated or the protonated or whichever adduct I found, I don't need to recollect data on another adduct in the next scan. Add matched fragments to dynamic exclusion allows you to say, I see these MS1 peaks in this MS2 spectra. They are probably in-source fragments. Don't bother collecting MS2 on them. Add passing search results to dynamic exclusion pairs up with that above checkbox for considering all the different precursors that were isolated, so that if it's got a match, even if it wasn't the initial precursor that triggered the scan, it was just something that co-isolated in the isolation window, you can still add it to the dynamic exclusion so that you're not targeting it again in a follow-up scan. The score thresholds set cutoffs either at least or beneath the values that you give it, and we'll talk more about what those individual score thresholds are in the next slide. But first, the final entry here is the compound class filter. this looks in the metadata field for a compound class within the library, then if your top search result matches the class that you list down here, you can tell it to auto promote or auto reject, which means regardless of what score it got, if the top hit matches a compound class of interest, you can say, hey, I always want to collect data on this if it's anything like this compound class. Or you can say, if you see this compound class, I'm not interested in it. Don't bother collecting any additional data. Next, let's talk about the 4 different score thresholds that you can set up in the filter. At the top here, we have the cosine score. This is a dot product of the intensity normalized spectra that tells the instrument how similar two spectra are in a mathematical sense. This goes from 0 to 1, and I've got a few slides coming up where I explain what this is in a little bit more detail. At number 3 here, we have the confidence scoring. This is a probability-based scoring algorithm put in to help reduce the likelihood of a false positive. Now what that means is it takes in 5 different pieces of data, including the cosine score, to say, how likely is this true? Now, I don't want you to think as you read this, oh, I see you have polarity of the query spectrum. Does that mean positive is more confident than negative? No, it's more of considering all 5 of these, how likely is this true? Like, if I've got a negative mode spectra at low collision energy, and I see tons and tons of extra fragments, that's not entirely likely. In my experience, things that are at low collision energy tend to have fewer fragments and larger fragments. So it's a way of saying, okay, I've only got one matching fragment. I'm not all that confident. I want to inform my follow-up scan behavior accordingly. At the bottom, in slots 2 and 4, are the delta scores. What this means is it checks the top result and the second result and calculates the difference between them. You can use this to trigger additional scan behavior based on how close those two top results are. Say if you've got 2 things with nearly identical cosine scores or confidence scores, you know you might need additional scans or additional information to tell those apart. And these are the scores that allow you to trigger that. Let's talk about what is a cosine score. It's also known as the intensity normalized dot product or cosine similarity score. Now, when I say intensity normalized dot product, that means the intensities of both spectra are added up and normalized to 1 so that they are more directly comparable. Now, a cosine score is a measure of the similarity between 2 spectra. Consider 2 very simple spectra. They only have 2 fragments in each, and they're at different intensities. We can think of each spectrum as a vector with x and y values proportional to the intensity of the corresponding x and y fragments. If we put those 2 vectors on the same graph, we can measure the angle between them. If we take the cosine score of that angle, it gives us a measure of how similar those 2 vectors, aka spectra, are to each other. A smaller angle between the 2 means the spectra are more similar. Consider 2 spectra that are identical. The resulting vectors sit right on top of each other. The angle between the two would be 0 degrees, and the cosine score of 0 is 1. This means the two spectra are as similar as possible. Now consider two spectra where the Y fragment is missing from one and the X fragment is missing from the other. The angle between these two vectors is now 90 degrees, and the cosine score is 0. This indicates that there's no spectral similarity between these two spectra. It makes sense. They have no peaks in common. Now, you could imagine this with more fragments. Say, with 3 fragments, you go to a 3-dimensional figure. And beyond that, it gets a bit harder to represent in a graphical form that we can picture. But know that this is basically what the math is following. How similar these two spectra are is the dot product between the two vectors that have been normalized to 1 that represent all the fragments in that spectra. Okay, now that we have an understanding of how the scoring works, let's take a look at how data collection differs with and without real-time library search. So without real-time library search, you collect ms to the 1, and then in a data-dependent experiment, you select a precursor, typically the most intense one, and you fragment it. Then, if you've got a complex method, like the one I showed earlier, without real-time library search, it will spend time collecting additional data on every cycle, regardless of how relevant that compound is to your overall study. In this case, that'll be a UVPD ms to the second experiment, as well as 3 data-dependent ms to the third. This uses a lot of instrument time and can make it very inefficient if you're targeting compounds that really aren't that interesting to you. So let's take a look at what it would look like if we added real-time library search. With real-time library search, the first 2 steps are pretty much the same. It collects MS1, then it targets a precursor and collects data-dependent MS2. Then we have a bit of a check. This is where real-time library search checks your MS2 and determines if this compound is interesting. It compares it against your library that you've provided, and if there are matching fragments, there's something similar there, it's interesting, it's worth it to spend the time collecting that additional data. However, if it's a complete mismatch, it's not so interesting. The instrument would be better off spending its time moving on to the next precursor so that it spends its time collecting data and finding those compounds of relevance. So how does this help a researcher? We know that every compound with enough intensity can be studied. Like with AcquireX, we can inject it multiple times and collect data. This data can include additional information like MSN and alternate fragmentation. We can make a very rich and expansive data set depending on how much sample and time we have. But that's just the thing. It takes time to study everything, and time is money and resources and complexity that you have to provide to dig through this more intricate data set. Real-time library search helps tell the instrument when it's worthwhile to spend time, so you don't have to go in afterwards and say, okay, I collected all this data, what in it is actually interesting, and what was just collected because the instrument didn't know why or when it should spend extra time. Think of it as giving it a statement that gives the instrument guidance on how you would like it to make these decisions. Like, don't waste time studying when we already have a competent annotation in the library. Or gather more information on compounds when they're in the specific compound class. Or I want you to run this experiment when the annotation is ambiguous between multiple choices in the library. Or even just, I have a precursor that's been metabolized. I want you to find everything that this organism turned this compound into. All statements where you can say, here is how I want the data to look at the end. That is how it is helpful to a researcher. Now, why would the researcher use real-time library search to accomplish this? Well, we know not every compound will be interesting to your study or need additional information. Your library represents your knowledge about what has been done before and what is important to you. So real-time library search is your means of taking that prior knowledge and telling the instrument how to use it. And doing this allows the instrument to make your final results more relevant to the questions you have about your samples. Now, there's a couple of experiments you can run. First off, we have an identity type experiment. In this experiment, you match the precursor M over Z, and you match the fragments. This is when you're finding an exact match in the library in either saying, this is confident, I don't need to spend additional time, or this is a good match in the library, but I want some additional information when it's matched. The next experiment is the one we're going to focus on more today, is a similarity type experiment. In this, we don't care if you match the precursor M over Z. We're only looking at the fragments. The reason being is those fragments tell you that there is some sort of structural similarity between the library and your experimental results. Now that we know how and why we would use real-time library search, let's take a moment to look at the scoring algorithms. Now, these tell the instrument how you want it to generate its scores. And there's some nuances between these two. The first here is called bidirectional or forward scoring. In this, your library spectra are compared to your experimental for missing fragments, and vice versa. Your experimental spectra is compared to your library, and the score goes down for missing fragments. Now, the reason I have forward scoring here in parentheses, this is not truly forward scoring. There isn't really a great reason to do a forward scoring experiment. And initially, when we launched real-time library search, we only had bidirectional scoring. But later on, we added reverse scoring. I'll talk about that in a moment. But because we had only a checkbox turned on reverse scoring, people assumed that without that checkbox checked, we were doing forward scoring. So you might hear them be used interchangeably, bidirectional or forward scoring. But really, if you uncheck reverse scoring, what you're doing is bidirectional scoring. Now, what reverse scoring is only looking to see which library fragments are present in the experimental spectra and not vice versa. To put it another way, in bidirectional scoring, we have these peaks highlighted in green. These are increasing your score. They match. You have these peaks in yellow, which are mismatches. Either they're in the experimental but not in the library, or they're in the library and not in the experimental. These cause the score to go down. Conversely, in reverse scoring, we still have the matched fragments that make the score go higher, and the library fragments that are missing in the experimental that make the score go down. But then we have the experimental peaks that are not found in the library. We don't care about these. So they don't get factored in when generating the score, so they have no impact on the results. Now, bidirectional scoring is going to be better suited if you want to do an identity confirmation. You want to know, is the experimental an exact match to the library? And you want only the best matches to get a good score. Reverse scoring is better suited for similarity matching. In similarity matching, you just want to know, hey, does this experimental spectra have all of my library fragments? Because my library fragments tell me the pieces of the structure that I'm looking for in the experimental. By doing it this way, if you have additional peaks in your experimental, say from an additional functional group being added on, you're not going to lose points for those extra fragments that are then generated. This brings us to our collaboration with Michael Christopher and Tim Garrett at the University of Florida. They wanted to collect additional data on indole compounds whenever they were found in their sample, which was a plant extract. This started when they provided us a library of indole-containing standards. This included biologically relevant compounds like tryptamine and N-acetyl 5-methoxytryptamine, better known as melatonin. We further curated the library by removing simple spectra. We only have 1 or 2 peaks. You have a lot of potential for false positives, so we took those out. Then we analyzed plant extracts with and without real-time library search in a similarity type experiment. And real-time library search was run either with bidirectional scoring or reverse scoring. Now, the first thing you get whenever you run experiments with real-time library search is a spreadsheet of the results from real-time library search. This is a TSV file that comes out in the same directory as the raw file. This gives you a list of scan numbers, what precursor massive charge was analyzed, what the top match from the library was, along with its formula, the time it spent to generate that score, as well as a list of the scores that were generated. So before you even get to your data processing software, you already have a spreadsheet with a lot of your results already listed. Let's look at the distribution of scores. So for bidirectional scoring, we had 6.6 thousand MS2 collected during the experiment. We can see that out of those thousands of scans, only 282 had cosine scores above 20. 20 was what we had determined empirically by looking in Compound Discoverer as sort of a threshold that anything beneath that has no real interesting similarity with the compounds in the library. And we can see out of those 282 that had scores above 20, 193 of those fell between 20 and 30. That's because anytime you had additional experiment fragments compared to what was in the library, that significantly reduced the score. You only get really high scores with bidirectional scoring if you've got a great match with your library compound. Conversely, if we look at reverse scoring, we had 5.3 thousand MS2 collected. Of those, 498 had cosine scores above 20, and they were much more distributed between 20 and 90. That's because your scores only depend on whether or not your library fragments are present in the experimental data. The big take-home message here is that because we're only trying to find things that are similar, bidirectional scoring can miss these similar compounds, because if there's any additional functional groups or changes in the structure that add additional fragments, that lowers your score and can potentially reduce your score so low that it no longer looks similar when using bidirectional scoring and they get missed. For example, we have an unknown at M over Z 271. We can see that when we look at the bidirectional score, we've got 8.6. It's very low. That makes sense. These spectra look nothing alike. There's not an exact identity match. There's a lot of extra peaks in the top spectra that are just not present below. The reverse score, however, is 77.7. The reason for this is if we look at what fragments from the library are present in the experimental spectrum, we can see that the top 3 most intense peaks are in fact present in that unknown. Does that mean that this is definitely a indole-containing compound? Not necessarily. But if I were looking at this data afterwards and I saw this level of similarity, I would want additional scans on that unknown so that I could make that call and determination after the fact. I wouldn't want to go back and have to rerun the experiment just to see if this particular unknown is as interesting as I want it to be. With that in mind, let's take a look at how real-time library search changed the instrument's time spend. Now we've got at the bottom of this graph all the different scans that it's going to run throughout the method. We're going to split these scans into two categories. On the left, we have MS and data-dependent MS2. We're going to call those binding compounds. MS finds the precursors, and MS2 gives us the initial information to tell us, is this a likely indole-containing compound? On the right is the additional information. This is the UVPD MS2 and the MS to the third that helps characterize those compounds later on when we're processing our data. We can see that without real-time library search, it spends most of its time on the right side of this graph, collecting the additional information. That's because you can see we've got a similar number of UVPD MS2 as HCD MS2. It runs everything in a brute force manner, regardless of how relevant that compound is. However, if we add real-time library search, a lot of that scan time moves back to the left side, finding those compounds. That's because it only collects the additional information when it's relevant. So we get a lot more MS1s and MS2s because it's not wasting its time on irrelevant compounds. But importantly, we still have the MS and MS to the third when we have a good match to the library, when it's most relevant to us. So we've seen how it changes how the instrument spends its time and how that changes the data. Let's now look at how that changes the final results. To do this, we process the data in Compound Discover looking for a few key metrics. Was data-dependent MS2 collected? Were there one or more known indole fragments? Indole fragments being, if you looked through the entire indole library, you would see these fragments popping up over and over again for these compounds. And finally, did we manage to collect additional data when there was enough information there to say this is a likely indole compound? So here we've got our metrics. With no real-time library search, we can see that we found the least number of compounds that are potentially indole, that we also had data-dependent MS2 collected on them. And we can see that with bidirectional scoring, we have the most number of compounds that we have MS2 collected on that are potentially indole. The reason for that, though, is we already know the instrument may miss similar compounds if they have additional experimental fragments. And that's what we see when we add the next bars. If we look at the number of those likely indole compounds that actually had MS to the third or UVPD data collected on them, we see that bidirectional scoring, which is looking for an exact match, missed a lot of those compounds. No RTLS found a lot of them. In fact, every compound that triggered MS to the 2 triggered these additional scans, so it makes sense they're the same number. But if we look at reverse scoring, we find 49% more compounds than no real-time library search, just because we are telling the instrument only collect that additional data when the compound is interesting to our study. So in the end, reverse scoring for this experiment made our results a lot more relevant based on what we wanted to know about this sample. So in conclusion, we gave a lot of detail on real-time library search on the Orbitrap IQX, and used that information to help a collaborator study indole compounds in a plant extract. We showed that RTLS focuses the instrument on what's most relevant to your study based on prior knowledge that is contained inside of the library that you provide. And we showed that reverse scoring is going to be better suited for similarity matching, where forward or bidirectional scoring is going to be a much better choice if you're trying to do an identity type experiment. I'd like to say a big thank you to all of my Thermo colleagues who helped make this work happen, as well as our collaborators, Michael Christopher and Timothy Garrett at the University of Florida. And I would like to thank you all for your attention. I'm happy to answer any questions anytime. You can reach out to me at brandon.bills@thermofisher.com. And this information is for research purposes only, not for diagnostic procedures. Thank you.